All right, welcome in everybody, 2 o'clock. Welcome back to your favorite class. Yes. Right, so agenda today, we're gonna finish up our statically indeterminate system conversation from yesterday. We're gonna start in on new material today, and it sort of piggybacks on the things that we've been talking about. So what we're gonna talk about today with trusses and frames is not gonna be in on exam number 2. So exam number 2 covers up to 3D rigid body equilibrium. So not trusses and frames, that'll be on exam 3. But we're going to start in on it today, and it's, tangentially related anyway, so it's good practice anyway. Homework 5 due right now. Hopefully you got that in. And a reminder, exam number 2 is this Friday. I'm not going to be able to do an exam review session this time, so sorry about that. Actually got kind of a family emergency. I'm flying to Pittsburgh tomorrow, so yeah. Sorry, guys. Exam 2 will happen this Friday. It'll basically take place the same way that we did it last time. You'll come to the Teams lobby, turn your camera on, point it at your workspace, and take your exam in the allotted time during lecture. So 50 minutes to do the test, 10 minutes to hand it in, just like you hand in homework, and that's that. So I'll post it right at 2 o'clock, and away you go. All right. So let's get back to where we were yesterday. So we were talking about statically indeterminate systems, and I had kind of left you with this example problem. And I was kind of asking you in this situation, which of these systems is statically determinate or indeterminate? And if it is determinate, calculate the reaction forces that are happening here. And we had done number 1 through 4, and we had sort of left as a cliffhangers 5 through 8. So let's go ahead and kind of round this out and finish this one off, and we'll talk about systems here 5 through 8 and what's going on. So let's go to 5. So sort of this truss arrangement number 5 here, not to be confused with Mamba number 5. We've got a pin in the lower left. We've got these two sort of bar reaction forces at the top and the bottom at B and C. And remember that these sort of bar reactions have a singular force in the direction of that link. So that's kind of what we were assuming for this particular problem. And we'll actually prove this mathematically to be true kind of in this lecture later. But each one of these links is going to carry one reaction force along the direction of the link. So if we thought about creating that particular free body diagram, we would have something that looks like this. Here's our pin at A. We had that reaction force here, just pointing upward at B. And we've got a reaction force here, pointing the X direction at C. This is a very interesting one because this particular situation, you've got, and we know this is 12, you've got what is 4 unknowns here, these 4 reaction forces, and we have 3 equations that we can work with. And interestingly, this one is actually underspecified, even though we have 4 unknowns. And there's a couple of ways that you can think about this, but the easiest is to understand that we cannot resolve the sum of the moments a day. Okay. And this is again coming back to this idea of like if you have parallel or concurrent forces, it can be a problem. And so here we have a set of concurrent forces here, and here we have a set of concurrent forces. All right, and this is problematic. And we see here that in this particular situation, if we were to try to sum the moments about A, we wouldn't be able to resolve this particular situation. This force and this force are both passing through A, and so you'd end up with something like sum of the moments A having an equation that is like only involving this particular value. And so that force there is 6 feet away. So you'd have something like 6 feet times 12 kip negative value. And this would be like your only moment about A that you would have. And so you would, in theory, set this to 0, but we know this is pretty obviously not 0. 6 times 12 is not 0. So we cannot resolve this like sum of the moments about A equal to 0. This sort of situation where you have something not equal to 0 most often comes up when you have like only 2 forces instead of 4 unknown forces. So it's a bit strange to have 4 unknowns and still see this sort of idea sprouting its head. And so here we are statically indeterminate. And we're actually underspecified here rather than overspecified. Okay, let's look at truss system number 6. Here we have this particular truss system here. This one is also a pretty interesting example. So we have a roller at A, a roller at B. So what would that look like? We've got our force that's acting downward at, our force P is 12. And we've got these two rollers that are only providing reaction forces upwards. So here, this is a particularly interesting case. And we hadn't really talked about this exact case, but in this situation, you've got 3 equations that you could possibly use, but one of your equations is like redundant, right? So something like sum of the forces x equals 0 leaves you with 0 equals 0. Okay, well, that's true. We don't have any forces acting in the x direction. So that equation is satisfied in theory for this particular situation, all right? Then you could go with something like sum of the moments about A equals 0. This gives you your negative 6 feet times 12 kips coming from this guy. And then you're going to have some moment contribution from, why did I write AX? This is BY. Some contribution coming from this force CY. This is 12 feet away from A. And it has the magnitude of FCY. And so we can solve for this reaction force and come up with this force at point C in the Y direction is 6 kips. Okay, so that's all good. And now with our sum of the forces in the Y direction, you could get that FAY is fully known, and this would also be 6 kip. Okay. So this particular situation, we would be fully determinant. So this guy here is statically determinant. But this is a particularly sticky situation because we have these rollers at points A and points C that are sort of supporting the system. And the idea is if this force here, this 12 kip force, were not exactly perfectly downward, then this truss wouldn't be able to stop any motion from occurring in like the X direction, okay? So this is a very strange case. And in the world of mechanics and dynamics, we would say that this is in an unstable equilibrium. This is probably a little bit advanced for this class, but you'll learn more about this later. Okay. And the idea would be that if you just perturbed that downward force even the slightest amount, your truss is just going to move. Okay. So think about something that's like sitting on ball bearings and you're holding it down and then you just like slide it left and right. That's kind of a situation that you sort of have here, right? So it is determinate, but it's an unstable equilibrium. It's like trying to balance an egg on a table, okay? If you don't have the weight of the egg directly right on the table, the egg is going to topple over. It's the same kind of idea, an unstable equilibrium. All right, moving on. Let's look at situation 7 here. So here we are with this guy. We've got this pin at A, and we've got these reaction forces here at B and C. At C, we've just got a horizontal force. At B, we have a force in this particular direction. And with this reaction force, we're going to have a singular force sort of in the direction of the link. And we actually can figure out what this angle is using some of the geometry of the problem. All right. So that angle there is going to be something like the inverse tangent of 9 on 12. So we could actually calculate what that angle is. So let's draw that in our free body diagram quickly. And then here we have this force that's kind of like acting up and to the right, which we might call the force at B. This is one singular force that's in the direction of that link. And we know that this angle theta is the same as this angle theta. It's kind of assumed from the image. And we have a situation where the angle here the tangent inverse, we know the side length is 9, the side length is 12. 9 and 12. This gives us an angle of theta in this particular situation, which is going to be 36.9 degrees. All right. So now let's go about trying to work through this bad boy. All right. Okay. Can't forget my force P here. I got to think, is this statically determinate or not? Well, it looks a little suspicious, but maybe we can sort of figure this out. Okay. Did I draw that right? I'm sorry, only a roller here. Yeah, it's a little suspicious. So there's no X component, only a roller there. Sorry about that. All right. So a couple ways we could go about this. I think the easiest way is to actually take a moment about C. So here's point C, remember? The reason I'm going to take the moment about C is because the line of action of this force and the line of action of this force both passing through C. So if I take the moment about C, the only unknown that I'll have is this particular force here. Well, if I sum the moment about C equal to 0, I'm going to have something like this force P here, which I know is 12 kips. That's 6 feet away from point C. Generally, this force is going to give me a positive moment about C. So we'll have something like 6 feet times the magnitude of that force, 12 kip. Then I have to include the contribution from this FIY. If I'm standing here at C, and I think about the contribution that FAY is going to give me, stick my arm in the direction of FAY, curl my fingers in the direction of FAY, my thumb will be into the board, or into the page. And that means that the contribution of that force as I have it drawn is going to give me a negative moment. So here we'll have something like minus the distance to that force, just 12 foot, times that force itself, FAY, is 0. So here you could solve for the force at A in the Y direction, given all of this information, would be here 6 kip. Okay. All right. Now with that information, I could go and solve the force at B in the Y direction using some of the forces in Y. So this is going to give me this FAY here up, which I know is 6 kips. This 12 is down, so minus 12. Plus the contribution from FB, which is in the Y direction. So this will be plus the force at B sine 36.9 degrees. All this together could solve that my force at B is going to be 10 kip. All right, so it's interesting. And then the last step here, you could also solve for the force at C in the X direction by doing some of the forces in X. So here, this is going to be like negative FB, since it's pointing to the left, times the cosine of this angle, 36.9, plus that force at C in the X direction equals 0. Those are my two contributions in the X direction. I know my FB to be 10 kip, so I could plug everything in here and solve that my force C in the X direction is going to be 8 kip. Okay, so this one, 3 reactions, 3 unknowns, fully determinant. Okay. And lastly, this guy. All right, well, we've got sort of a pin down here in the lower left. We've got a single reaction force upward at C, and we've got this angular reaction at B that's happening. Okay. So here, my free body diagram. I've got this reaction up at C. I'll get this reaction here. And I had a pin at A. All right. So maybe I just try to go about my business. I see that I have 4 unknowns here, so might run into some problems. You could start with some of the moments about C. That would get you the force at A in the Y direction. Hopefully we can sort of see that. If you did the moments about C, which is here, the only contributing factors are going to be this 12 kips and this force at A in the Y direction. So you could immediately get your FAY from that particular set of equations. But now some of the forces in X and some of the forces in Y cannot resolve the remaining 3. All right. So you could sort of maybe figure out what that force at A in the Y direction would be. Sorry. But you would still have 3 unknowns here and 2 equations that you couldn't really resolve. All right. Unfortunately. So this is indeterminate. Okay. Now I know I went through those rather quickly. Hopefully we're getting comfortable, 2D equilibrium, comfortable enough where this sort of makes sense. But the point is you have to be on the lookout for situations like this, where you have some equilibrium set of equations and you've got more unknowns than you can deal with your equations, or you don't have enough unknowns to satisfy all the equilibrium equations that you have, meaning you would have some degree of freedom in your system that would not, enforce equilibrium. All right. Okay. So that'll end our discussion on strictly 2D and 3D equilibrium. So everything up to now, game for the test. But now we start on a new topic. And that new topic we're going to start is trusses and frames. So let's go to that. Man, handwriting today. Too much coffee. All right. Trusses and frames. And I'm just going to bring in a picture from the lecture notes. I posted a new set of notes on Canvas if you want to take a look at those. I'm just going to bring in the first title frame here. So here we have trusses and frames. And we've sort of talked a little bit about trusses already. I mean, the example problem we were just working on was an example of like a truss in space and all the reactions that were sort of holding that truss in place. But now we're going to dive a little bit deeper on trusses and later on frames, which are similar. The idea here is that if you have some structure that's made up of many, many members, like a truss, each one of those members can be analyzed individually with its own sort of free body diagram. So if I were thinking about, this frame truss assembly here, I could create a free body diagram of this whole thing by sort of isolating it with our traditional methods where I sort of, kind of draw a line around this guy, cut away the reaction at A, think about the weight at W. You would have your traditional free body diagram for this guy that looks something like this. And away you go, okay? You calculate what the tension is, you calculate AX, calculate AY using all the sort of tools that we've talked about so far. But beyond just the whole body as, its own free body diagram, you can also think about isolating individual members of this truss, okay? And the way that you might do that is by considering like all of these points on the structure as individual pins that might have their own like reactions associated. And so if I wanted to think about like separating this long column here from those other pieces, well, I've got a pin here at C, and so I could represent the reaction forces at C with, let's say, 2 forces at this particular pin. Okay, so it's very similar to a pin that might exist on sort of an external side of your body. You could think of having a pin on the inside. All right, so we've got to talk about how we do this and how we execute. But I do need to introduce one preliminary idea before we dive in full force on trusses, and that is the idea of two force members. So let's do that now. All right. And for two force members, I want to consider any rigid body that only has two forces that are acting on it. So say you have some skinny rod or even an L bracket of some kind. So let's consider an L bracket with only two forces acting. Okay. So here's your L bracket that exists in space. All right. And let's say down here is point A, and over here is point B. All right. And let's now consider two arbitrary forces that are acting on this particular object. So F1 and F2 act at A and B. So here's F1. And let's say you have some arbitrary F2. Okay. If this structure is in equilibrium, we can make some assumptions about what's happening with those two different forces. Specifically, if you only have two forces acting on a member, then there are some very specific things that you can know and understand about these two forces. Okay, so if this object is in equilibrium, we can enforce restrictions on F1 and F2. Okay, so what do I mean here? Well, if we were to, let's say, sum the moments about point A, so if we here sum the moments about A equals 0, and we are enforcing this to be true on our object. We know our object is in equilibrium, so we are enforcing that. If we need this to be true, then we're going to have something like, if this is our position vector, which locates F2, only true if the position vector arriving at B from A crossed with the force 2 is equal to 0. Hopefully we see and understand that. Whatever force is happening at A, force 1 is passing through A. So there's not going to be any contribution to the moment from that force. The only possible force on this structure which could contribute a moment about A is this force here. But if we're enforcing equilibrium, that means that this particular portion, which is the moment that's created by that force number 2, has to be 0. And there are only two situations where that particular cross product could be 0. Situation number 1 is that obviously the force is 0, which is like a trivial solution we don't really care about. And situation number 2 would be, there's 3 possible solutions, is that our position vector to that point is 0, meaning that point A and point B are the same point. Okay, that doesn't really mean anything, also a trivial solution. Or also that the magnitude of this cross product is equal to 0. And remember that the magnitude of this cross product is like the magnitude of R multiplied by the magnitude here of F2 multiplied by the cosine of the angle between the two. Cosine? Sine. I always get my dot product and my cross product mixed up. Yeah, right. Okay, So if we care about a situation where we're enforcing this equilibrium, then the only situation where this could be true is if this particular cross product is equal to 0. Or what we're saying is if the position vector is not equal to 0 and the force vector is not equal to 0, then the only situation that's true is when the sine of this angle theta is equal to 0. And that is that the line of action of F2 is directly along the line of R. So for this to be true, line of action of F2 must be through point A. So if I think about that pictorially, oh, sorry. Here's my L bracket. Again. Here's point A. Here's point B. And again, we'll consider some force out here that's F1 is still acting on our piece. And so the first enforcement that I have, if this thing is going to be in equilibrium, is that the line of action of F2 must be along the line that connects A and B. So if we think of this dotted line as the line of action that connects points A and B, if the sum of my moments about A has to be 0, it's what we're enforcing for equilibrium on this bit, then F2 must be on this line of action, either in this positive sense or the other direction, the negative sense. Okay. Also, if I'm going to enforce not just moment equilibrium, but if I'm going to enforce force equilibrium, I have another restriction here on my piece. This must be true. So if we're summing our forces and the sum of those forces must be 0, then F1 must be exactly the opposite of F2. Otherwise, if you sum the forces, it's not going to be 0. Okay. So that restriction, if we're in equilibrium, that forces this situation. Here's point A. Here's point B. We know because of like the first restriction that force number 2 needs to be on this line. That's the restriction that comes from the sum of the moments about A equal to 0. Now, to also enforce my force equilibrium, that is that the sum of the forces has to be 0, the force at A must also be along this line in the opposite direction. Okay. Okay. So what does that mean? So finally, if a rigid body only has 2 Forces acting at two separate points. Those reaction forces must be along the same line. And must be equal and opposite. This is very powerful when it comes to truss analysis, because when you're looking at trusses, there are going to be a lot of members that are contained inside of your truss that are basically pinned at two opposite ends, okay? And if you have a member that's just pinned at two opposite ends, well, you know that the force that are at those two opposite ends has to be equal and opposite to each other, okay? We actually saw an example of this in the very first slide that I showed in these lecture notes. And that would be this member here, member BE, inside of this structure. Okay, if I were to look at or isolate that particular member, I only have reaction forces that would occur at point E and reaction forces that would occur at point B. So neglecting the weight of this particular object, if I were to isolate this from its surroundings, I would have like a pin at E and a pin at B, which typically would be like two reaction forces for each one of those locations. But because of what I just talked about, there really is only an equal and opposite force which occur on either end of that member. So here we are with this particular member, if it's isolated, and you see this free body diagram of this particular member only has those forces that are acting along the line of that member, okay? And we see that they're along the line between point B and point E, and they're equal and opposite in magnitude. And so this will come up pretty frequently when we look at trusses, obviously. All right. So finally, let's move on. This whole section is on trusses and frames and machines. And these actually have very specific definitions in mechanics. So let's actually define what is a truss, what is a frame, and what is a machine. Okay. Truss. All right. A truss is like a stationary, fully constrained structure, a bridge, for instance. Okay. Okay. It's almost exclusively made of straight members that connect at joints. Right? Many two-force members. Right? Let's look at an example of what a truss might look like. Here's an example of a very simple truss system. So here we are. Very straightforward, very simple. It's made of a number of straight members, connected at joints, connected at pins. A number of two-force members here. So like this guy here, two-force member, right? Just two forces acting on that guy. This guy, 2-force member. 2 forces acting on that guy, so on and so forth. Pretty easy to see that there's a lot of 2-force members in that piece. This is differentiated from a frame. Frame is similar, and I would say a truss and a frame are interchangeable vocabulary, but they differentiate in your book, so I'll do it as well. Typically stationary as well. But has one or more multi-force members. Not usually. Has. Okay. So, and then example frame would be one like we saw at the very beginning of lecture on slide number 1. Here's an example frame. He framed me. Okay, so this differentiates from a truss because there is a member on this particular frame that has multiple forces running through it, and that would be this member here, ABCD. Okay, so we've got a number of reaction forces down here at A, got some reactions at B, some reactions at C, and a tension here at D. So it's obvious that that member ABCD has multiple forces acting on it. It's a differentiation from our truss above, where each one of these guys really only has, 2 forces acting on it. So here's your example frame. This also has multiple forces acting on it. This piece, the CEF. Okay. Why does this keep jumping? I've got like the force associated here. I've got the force here. I've got the pin here. All right, a variety of different forces acting on CEF. So that is also not a 2-force member. All right. Lastly, are your machines. And machines differentiate themselves because they typically are not stationary. Okay, so they're designed to move. Okay. So most of the machines you'll talk about when you're a student at MSOE are going to be reserved for like your dynamics classes. Okay. But there are some situations where a machine might be stationary and be useful to analyze in this class. And we'll see an example in just a second. Typically, many multi-force members. All right. Basically, any tool that you could think of is probably a good example of a machine. All right. I have a simple example of a set of pliers here as my example machine. But if you were to sort of like isolate, let's say that there was some rebar that you were cutting through or something right there, some wire that you were cutting through. If you were to isolate that particular machine away from that thing that you were cutting, well, you would see that they would be providing some reaction force to you in these opposite directions. And your hands that were sort of working on this other side of the pliers would be applying some force on the pliers to do what you need to do to cut that thing open. All right. We're going to, take a look at this machine in a little bit more detail in an example problem later in the course, but this can be broken down into like 2 different pieces, which would be like sort of like an upper handle and like a lower handle, right? So you can break this up and analyze both of these pieces separately. Where here's like the pin at A that you would have like reaction forces that are occurring here, as well as the reaction force down here at Q and the reaction force down here at P. Okay, so you can break this up into sort of multi-bodies, and we'll do that a little bit later in the course. All right. And I'd say that these get sort of more and more complex as you move through. So trusses are going to be the easiest to work with. Frames a little bit more complicated because you have multi-force members. And then machines, I think, would be the most complicated. Okay. Yeah. So let's keep going. And we're going to dive in now on trusses. All right. And specifically, we're going to focus on free body diagrams of trusses. All right. And remember that these almost always consist of two force members. So if you're ever kind of stuck on the analysis of a truss problem, you really need to think to yourself, am I working on a member inside of this truss that only has these two forces passing through it? You know, if you're like thinking about a pin inside of a structure that has multiple forces, you might want to stop and think about, are there actually forces in multiple directions here, or is it just along the segment of this truss? So, okay. All right. Your free body diagram of a truss is going to be typical of what you see in 2D equilibrium problems, okay? So nothing really crazy about the first step in analyzing a truss. Of whole structure. Okay. So this would be like an example. Okay. If you had, for instance, that truss that kind of we showed before, and the example that had all these members in it. Let's say this was your particular truss system, and you had a pin here, and you had a roller here, and you had a force that was acting here. B. Let's say that this was your truss. Your first step in the analysis of this guy would be your typical 2D equilibrium analysis, and that you'd make a free body diagram of this and figure out what the reaction forces are. Oh boy. And so you would do something that looked like this. Here's your truss. Isolate your reactions. So isolate the truss from the reactions. And so here you'd have some force that acts here. You'd have some force that acts here. And you'd have some force that acts here. So if I call this here point A, call this here point B, then you would have a force at A in the X direction, force at A in the Y direction, and a force at B in the Y direction. And you could do your equilibrium analysis and calculate what these forces are at these various reactions, okay? So you go from a situation where those reactions are unknown to a situation where they are now known, okay? After you have calculated these reaction forces, which are kind of acting on the outside of the truss, then you can start analyzing individual pieces inside of the truss and sort of propagating information away from those reaction boundaries that you know. Okay, so then you can start sort of like isolating individual bodies or individual components inside of the truss. Okay, for example, if we had up here, let's call this point C. Okay. So an example, rod AC. Here's point C. Here's point A. You could isolate this individual rod from the rest of the structure by thinking about sort of like isolating this guy from its surroundings, like so. Okay. When I'm doing that, I'm like cutting through this member, cutting through this member, cutting through this member. So I have to account for the forces in each one of those individual members that are resulting when I sort of isolate rod AC, as well as the reactions that would occur at A. So when I think about isolating rod AC, I still have those reaction forces here that are now at A. And since I've sort of like cut through some of those other pieces, that would be like, again, back to my example here. Since I'm isolating or cutting through here, I'm cutting through here, and I'm cutting through here, I have to associate or include the forces that go along with those particular members as well. So here, I might have another force that's acting horizontally from that guy. I have a force that's acting vertically from cutting away that central pillar. And then I also have this force that's acting over here from cutting away sort of that third component. So if I want to put some label to these and I say like this is point D, then I might label this as like FAD. It's the force that points from A to D. I might label this as FCD. I might label this as FCB. It's the force that points from C to B. And from my sort of equilibrium analysis, I know these guys already, okay? Now I can enforce equilibrium on this particular piece alone, because I know it's not moving. Do the sum of the forces, do the sum of the moments on this particular piece alone, and you could calculate, all right, what is the force in rod CB? What is the force in rod CD? What is the force in rod AD? By my equilibrium analysis, okay? I would have 3 equations and 3 unknowns to work with on this particular free body diagram, okay? So you're isolating this individual component, but in doing so, can calculate sort of the forces that are running through the other members of the truss. Okay. So I think that's where we'll stop today, and we'll actually do some practice problems with these ideas tomorrow. So that's it for today. We will see you tomorrow.